Today's lesson is on colligative properties of solutions. What is a colligative property? Colligative properties are physical properties of solutions that depend only or solely upon the amount of solute particles. And solute particles, once again, can be molecules or ions within the solution and not at all upon the type of solute present. This just means I do not care what it is that you dissolve into water. I do not care if it is ionic, covalent, whatever, but it's going to affect the physical properties of that original solvent itself than if there were nothing in there to begin with. Okay, it does not matter what that type of particle is that's dissolved as the solute. It just matters how much of that solute that is present. Okay, so the way to kind of explain this is when I have a solute being added to a pure solvent, the added solute particles, y'all, they're going to get in the way in some way, and they will disrupt the normal activity of the properties of the solvent. Okay, so the little blue guy says, we are water molecules, and we like our normal order and behavior. This little hexagon guy says, we are glucose molecules, and we get in the way and cause disorder. Uh-oh. Well, now the number of solute particles in the solution will correspond to then how much disruption occurs. So the water molecule says, what is happening? Glucose says, the more of us that there are, the more we get in the way. More disruption, you guys. Oh my goodness. Water molecule says, I give up. And then glucose says, this is the glucose show now. All right. So in calculations involving colligative properties, we actually use little m molality to measure the concentration or the amount of solute in that solvent. The higher the concentration, which means the higher the molality, the more disruption the solvent will experience from its normal typical behavior. Okay. So solute disrupts everything that the solvent usually is expected to want to do. Okay. We're actually going to be discussing 3 properties today. There are technically 4 properties. The first 2 are the main ones we're going to hit, and I just realized that I've numbered these 1, 1, and 1. I guess that just means the order of importance, which means they are all important. We're going to focus, though, mainly most of our time on boiling point elevation and freezing point depression. But the last one we'll also zone in on slightly is vapor pressure lowering, which is exciting. Okay, let's start with boiling point elevation. You know me, I like to kind of abbreviate things because I do not like too many letters of the alphabet. So if you see me saying BPE, that just stands for boiling point elevation. So this is our first colligative property. So the way this works is when a solute is added to a solvent, the solute particles will interact in some way with that solvent. Now, these extra interactions, or oh my gosh, you guys, maybe IMFs between the solute and the solvent, mean more energy must be gained to get those solvent particles to a point to where they can boil. So this actually raises the boiling point. Therefore, the boiling point of the solution, meaning when the solute is actually in the solvent, when I have a solution going on, that boiling point will be higher than that if I just only had pure solvent. So the more solute particles I cram into that solution, the more interactions between the solute and the solvent. Therefore, the higher the boiling point, the higher the energy that's needed to get them to overcome those interactions in order to go from a liquid to a gas state. Okay, so the trend here, or the mentality of the way that boiling point elevation works, is that the more solute I have, you guys, the higher that boiling point will be raised in that solution. So here's a visual. This, I'm assuming, is to be water. The pure solvent of water, I can see it transitioning from the liquid phase to the gas phase quite nicely. But if I add something into the water, meaning I have a solution of not only the water solvent, but also now the solute in some way, I see those solute particles in here. And oh my gosh, there's opportunity for some interaction with the solute particles to where that they are not quite as easy to escape the solution in order to boil from a liquid to a gas. Okay, so I'm creating fewer gas particles here, meaning it's going to take more energy for them to turn into the gaseous phase. All right, very cool, very fun. All right, so I told you there's some calculations on calculating BPE, or boiling point elevation. So I can calculate the magnitude of boiling point elevation, meaning how much that original boiling point will be raised by, using this equation. Delta TB, which stands for the boiling point elevation. This is technically the difference in temperatures between the boiling point of the pure solvent on its own and the boiling point of the solution, meaning with the addition of solute in it. Okay, so to figure out what that change is, that magnitude of change, that boiling point elevation, that's going to be equal to IKBM. I stands for, it's technically the Bent Hoff factor. It's just how many solute particles are going to be present in solution. We will talk about the possibilities of how to figure out what I is a little bit later, but that's how many solute particles you're going to get dependent on what the solute is. KB is a constant. We love a constant, which means I will feed that to you on a platter. It is the boiling point constant of whatever that solvent is in its pure state. And then little m, we've seen this before. This is molality. And once again, molality is the number of moles of solute over the kilograms of solvent. So here what we have here is a phase change curve, okay? I have me transitioning in temperature, what happens, and this would be the boiling point of my pure solvent. Let's just say it's water at the standard pressure, okay? So whatever temperature that solvent boils at would be like its normal boiling point. For water, it would be 100 degrees Celsius. But if I put some solute in there, I now have a solution. I notice that, oh, wow, now it boils, meaning I go to 1 bar at, a higher temperature. So this is boiling point elevation actually like visualized here on a graph. That distance, or that difference between those two temperatures of the pure solvent and the solution now is going to be that change, that delta TB. Okay, so let's do some practice examples. I feel like doing some practice examples. All right, so we're going to be using this equation and seeing how well we can actually do here. Okay, the first one says, what is the boiling point elevation of a 4.00 molar aqueous solution of cesium nitrate? Kb of H2O is 0.52 degrees per molal. Okay, so what are we even solving for here? What is the boiling point elevation? Boiling point elevation, boiling point elevation, y'all. Boiling point elevation is the change in temperature from the original boiling point to the new boiling point now that I've introduced solute particles. So I'm actually just literally solving for delta TB, which is really good for me, of a 4 molar aqueous solution of cesium nitrate. So I'm giving you the concentration of how much cesium nitrate is in that aqueous solution. So this is my molality that I'll be using for my calculating boiling point elevation. Okay, and then they also gave me the Kb of water. We know the Kb is the constant depending on what the solvent is. We said it was an aqueous solution. Aqueous means that the solvent is water. So this is what I'm using for my Kb value. Okay. So, looking at my original equation, we know my original equation to solve for the boiling point elevation is delta TB is equal to I KBM. Well, we have the Kb and we have the molality. What we are missing here is the I. I stands for how many solute particles will be present that solute contributes when it gets into solution. You're like, well, what does that even mean here? Well, first of all, it has a lot to do with, number one, are you ionic or covalent? Covalent compounds, when you put them in water, they do not dissociate into more than 1 particle. So if I had something covalent going on here, its I value would be just 1. There's 1 particle that is represented in that solution per particle of that solute going in. But my ionic compounds, not so much. We know if they're soluble ionic compounds, they do that fun thing where they dissociate into their respective ions in solution. So we're going to have to figure out a dissociation equation for my cesium nitrate and figure out, well, how many particles are being dissociated from that process. So I can say, to dissociate cesium nitrate, he will break apart into ions. He will break apart into, it looks like, 1 cesium ion, which cesium is a group 1 metal. He's a +1 charge. And if, as a reminder, nitrate's a polyatomic ion, so that entire thing will dissociate as one thing with a -1 charge. So it looks like I have 1 positive cesium particle and 1 negative nitrate particles. So therefore, we could say my I value is equal to 2. So this specific ionic compound dissociates into 2 particles in solution. So that's how you figure out your I constant, which is our I value, which is really cool. That does depend on what type of solute you have. All right, so now we're ready to plug in and solve. So my I is just 2, like literally the number 2. There are no units for that. We counted 1, 2 things. Amazing. My KB value is 0.52 degrees Celsius per molal. And then finally, my molality is 4.00 molal. Okay, so I grab my calculator. I'm ready to go. Let's see. Have everything written down correctly. So I'm going to say 2 times 0.52 times 4. Cool, amazing. All right, it looks like everything is 3 sig figs in here. Constants are not ever to be considered for sig figs. They're what's called infinitely significant. If I've given it to you, I'm sure of the exactness of that number. So really the only measured value that we have in here is the 4.00 molar. I constant, it's just me a counting number here, okay? So that is not a sig fig consideration. So the molarity has 3 sig figs. That means my answer needs to be rounded to 3. Y'all, it's already 3 sig figs. We are in luck. That is super exciting for me. So 4.16. Well, this is a temperature, so I'm really hoping, and you can even look here at my units here. If I cancel off a molality on bottom and a molality here on top, the only thing left over is a degree Celsius, which hopefully makes sense for a temperature. So like, I want to kind of break down, well, yes, this is my answer. This is my boiling point elevation, or the change in magnitude by how much the boiling point would be raised. So let's like break down what information we can get from this. It's kind of, it's not silly, but it would be maybe silly for me to be like, here, what's the boiling point elevation? We tend to take it a step further and being like, well, what does that actually mean in terms of how would this affect the original boiling point to what amount? Well, that's what brings me down to example number 2. It says, well, what is the boiling point of the solution in example number 1? Oh, well, it's water. We know water's original boiling point is 100 degrees Celsius. So that may be something of interest for us to write. So we could say normal BP of pure H2O is equal to 100 degrees Celsius. And the trend here is, or the colligative property is boiling point elevation, meaning if I put solute into a solution or a solvent, we raise the boiling point, okay? So something of note is that I would say adding solute raises the boiling point. What we have calculated on the previous problem is, oh my gosh, you guys, by how much I have raised my boiling point. So here when they're asking for solving just what is the boiling point, meaning the temperature at which it boils, no longer the magnitude of the change in the boiling point elevation, I just get to add that value to 100 to figure out what this temperature at which the solution would boil. So I can make this statement, that temperature, that new boiling point would be equal to 100 degrees Celsius plus whatever that change or that boiling point elevation that I saw for in the previous problem, right? So all I'm doing here is 100 plus 4.16 degrees Celsius. I do not even need to use my calculator. That is literally 104.16 degrees Celsius. Okay, so that means by adding that amount of cesium nitrate, I now have a new boiling point for that water, or that solution containing water, of being 104 degrees Celsius. So we actually see this in the real world. A very common thing that we do when we boil a pot of water on the stove for cooking is we add salt to it. And the most common kind of misconception here is that people think, oh, I'm adding it to make it boil faster. You are actually not even anywhere close to doing that. But what you are doing is you're making the water that you are hopefully cooking with, like making pasta with, hotter. Yeah, that's going to cook your pasta faster, okay? Because adding salt to that water means it's harder for that water to boil. It is no longer going to boil at its normal 100 degrees Celsius. You may have water that's sitting there at 105 degrees Celsius or 110 degrees Celsius, which, yeah, does a better job of cooking our food. Okay, so that's boiling point elevation. What is another colligative property? Oh, here's another good one. Freezing point depression. As a review, freezing point is the temperature at which something freezes. That is also the same equivalent temperature at which something melts. We typically in science refer to that temperature, which is the difference between the phase changes of solid to liquid to solid, as a melting point. The reason why we're specifying the opposite direction, which you're like, what is even happening here, is because we see this effect in the property when specifically going from the liquid phase to the solid phase. Anyways, I just wanted to clear that up. I feel like that was a tangent. Anyway, let's see. So freezing point depression, or FPD, like the way I like to call it, says when a solute is added to a solvent, the solute particles, you guys, they can kind of act as obstacles between all my solvent molecules. So these solute particles will actually disrupt any orderly stabilizing IMFs between my different solvent molecules that would be normally required for them to kind of assume their positions to freeze. Okay, so if I'm looking here on my temperature, first I thought this picture was kind of confusing to see. So this is just showing that my temperature at which I freeze for my solvent is higher than if I have solute particles in solution. So this is just the pure solvent. Now when I freeze, we know that they get close together in the solid phase and kind of make a crystal structure. Okay, well that's going to require all of my solvent particles to snuggle on in tight. Well, if I put a solute in there, y'all, they are straight up in the way. My water solvent particles are trying to sneak on in there and get with their water buddies and freeze, and they can't because there's some ding-dang solute particles in the way, and that is not convenient for them. They are probably very upset about this. Okay, so as a result of this, it means there's got to be more energy to be lost to get these solvent particles to finally get to each other and freeze. So this actually lowers the freezing point, meaning it's going to freeze at a much, much lower temperature than it should be. So the freezing point of this solution is going to be lower than that of the pure solvent. And the more solute particles I have in solution, y'all, the more they're going to get in the way, the lower and lower and lower that freezing point will be. Okay, so the more solute you add to your solution, the lower and lower that freezing point. Okay, this picture is a little hard to see, but what I'm looking at here is my pure solvent of water and it turning into its solid position of that wonderful crystalline structure of forming the hydrogen bonds in between the different water molecules. Now, if I stick some of these green particle solutes in there, water is like, hey, you're in the way between me and the other water molecule. We got to do our thing, our hydrogen bonding thing, to get to freeze. And that is not a possibility for them. So it's harder for them to try to get to that freezing pattern. Amazing. Okay, just like my boiling point elevation, I can calculate freezing point depression, meaning how much that freezing point will be depressed or lowered by. This equation looks kind of similar, right? Yes, it sure does. And it works kind of the same way. All right, so the delta TF is the freezing point depression, meaning that's the temperature difference between what the freezing point for the normal pure solvent is and the solvent when it is now mixed with the solute or the solution, okay? I is once again the number of solute particles that the solution has. Okay, we figure that out in terms of whether it's ionic or covalent, and if it's ionic, we figure out how many ions it dissociates into. Kf is a constant, is the freezing point constant of whatever that pure solvent is, and then M is molality. Okay, so here on my phase change graph, if I were to focus on the liquid solvent, meaning just the solvent, the temperature at which it freezes would be right here. But if I add solute particles to this solvent to make now a solution, oh my gosh, you guys, the temperature at which it freezes has been lowered in some way. So the delta TF, or the freezing point depression magnitude, is represented by the difference in those temperatures. Okay, so let's practice doing an example now. Just like we did with our boiling point elevation, we are going to figure out some freezing point depression for us. Okay. Oh, these are fun. I like these. Okay. What is the freezing point depression of an aqueous solution of 3.5 molar zinc phosphate? And the Kf of water is 1.86 degrees Celsius molal. Okay, so when I ask for freezing point depression is by how much does that freezing point depress or lower by. So I'm literally calculating the delta TF. I'm calculating that guy right here, okay? Well, I know the equation for this guy is very exciting. Delta TF is equal to I Kf molar, or molal, sorry. So I'm like, okay, I hope I have all of those things. Yes, I do have a 3.5 molal solution, and it is an aqueous solution, which means my solvent is water. Did they give me the Kf for water? They sure did, okay? So what I have here is I have my Kf, I have my molality. The only thing I'm missing is, my Van 't Hoff factor. How many particles is this going to dissociate into when it gets in solution? It is an ionic compound, okay? So that means it will dissociate in water, which means I can write a dissociation equation. So this soluble ionic compound, this is going to be a fun one. I threw a fun one in here because I thought it would be fun. It's all fun. Okay. Let's see, how many zincs do I have here? I have 3 of them. And when this ionic compound dissociates into its ions, it will dissociate into 3 zinc ions, each one with a +2 charge. And the phosphate polyatomic ion is also represented. I have 2 total phosphates. So I would say 2 PO4, and each phosphate has a -3 charge. Okay, so looking at how many total ions I have in solution, how many total particles, 3 + 2. That means my Van Hoff factor, or my I, the number of particles that are created from solution, is 5. Okay, so I got 5 going on here for my I. So we have an I, we have a molal, we have a KF. We are ready to plug in and solve. I is the number of 5. KF, we said for water, was 1.86 degrees Celsius molal, or per molal. And then finally my molality is 3.50 molal. Math it up, see what we get, see what we get, see what we get. So we have 5 times 1.86 times 3.50 equals. Okay, so that's my answer. 32 point, let's sig it out. We talked about my KF or even my KB values. Those are constants. Constants are always infinitely significant. That is a counting number of 5. You are sure that that is exactly 5 things that I've written here, meaning the only measured value from the problem that I have to consider is that molality, which is 3 sig figs, which means I need to round this answer to 3 sig figs, which means 32.6. This is a change in temperature, so it will be degrees Celsius. So this is the freezing point depression. It represents the magnitude at which that freezing point of water will be depressed by now that it has a solute incorporated into its solution. Okay, so what does this mean in terms of what is my solution going to do? What is it going to freeze? Well, let's see. It says on example number 2, what is the freezing point of the solution in example number 1? Y'all, I'm having you solve for the freezing point. Tell me, please, what is the new temperature at which this thing freezes? Okay, well, let's map it out. The normal freezing point, or normal melting point of water, is 0 degrees Celsius, right? So let's go ahead and state that just for funsies. Normal FP of H2O is 0 degrees Celsius. Okay, and is it elevating that freezing point, or is it depressing? Boiling point elevation, freezing point depression. So this lets me know that adding solute, meaning adding something like a zinc phosphate, will lower that freezing point, which knowing that a freezing point will be depressed or lowered means I can make this fun statement. Well, to find the new freezing point of my solution, it's just going to be 0 minus whatever I solve for when I solve for my delta TF. Yes? So let's see. We have 0 degrees Celsius minus, and 32.6 degrees Celsius, right? So it looks like my new freezing point of this solution is negative 32.6 degrees Celsius. So that water will not freeze until you get below, much further below its typical freezing point. So that's super exciting. Okay, y'all probably seen this concept of freezing point depression in real life, especially during the winter. We know that when it snows and the roads get icy, we do this real fun thing like put salt on the icy roads. And yes, the salt does make it less slippery because you got something now crunchy here to drive on. But it also being added to the ice, it confuses that water in the ice to be like, wait a minute, we got something in us. We should not be freezing now. So it lowers that freezing point to where that ice will actually melt into water by depressing the original freezing point. Okay, it makes the ice like think I'm not cold enough to freeze and stuff yet. So I need to continue to be in the liquid phase. All right, so here's something cute. Friends keep you from freezing, okay? They lower your freezing point, okay? So here's my solutes. And the term non-volatile just means that they are not evaporative, which means they will stay in the liquid phase. But here, my little water molecule is surrounded by solute particles who are keeping him from freezing. Also keeping him from boiling. We know both can be true now, okay? All right. Vapor pressure lowering is our third one that we're talking about today, okay? And the only reason why I'm talking about just vapor pressure lowering and not the fourth colligative property, the fourth colligative property is osmotic pressure. It's just this is a really easy tag on here, this vapor pressure lowering, a tag on now that we have learned about boiling point elevation. We're not going to do too much with it. We're just going to focus on the first two. But here we go. Vapor pressure lowering. In a solution, the presence of solute particles, we know, means more energy must be gained or lost to get the solvent particles to boil, raising the boiling point from that of the pure solvent. This first statement is just saying, hey, y'all know about boiling point elevation now. Yes? But as a result of that boiling point being elevated, less solvent will evaporate into the gas. And therefore, if I have less stuff in the gaseous phase, I won't have quite as much vapor to apply a pressure, right? So this lowers the vapor pressure. The more solute particles in solution, the lower the vapor pressure. Okay, so here my pure solvent of water, we know if I do not have anything in and disrupting the nature at which water behaves, that it will evaporate and turn into a gas at whatever its boiling point is. But now that I've incorporated a solute here in this picture, it struggles to boil, right? It's going to take more energy. It's raising that boiling point, which means I have less vapor particles, which means my vapor pressure is not quite as significant, just strictly because I have less solvent in that gas phase. Now, can I calculate vapor pressure lowering? I sure can. You can calculate vapor pressure lowering of the solution with Raoult's law, and you will have to do this at some point maybe in your chemistry career. We are not doing this today. That is for something for you to look forward to later, okay? Calm down and stop trying to evaporate. Here are your non-volatile solutes here. They're going to lower your vapor pressure. They will not want you to evaporate, which is really, really funny. So the thing here with my colligative properties is that, y'all, it doesn't really technically matter what it is. Is it sodium chloride? Is it potassium chloride? It doesn't really matter what that substance is because they're not involved in any chemistry when I'm making a solution. We've talked about before, making a solution is a physical process, right? So depending on what the chemicals are is irrelevant. We just want to know how many of them I have in solution, okay? The amount is what determines how much that freezing point will be depressed by or how much that boiling point will be raised by, right? So these are colligative properties, strictly figuring out how solute interference can affect some of these physical properties of a pure solvent.